Okay, so we'll come back to the question number 2. And here we are going to do the calculation for the pouring calculations. To give you an example about the pouring calculation, what we are going to have is a gating system, or the, maybe it's going to be a gating system, which is the channels that required to take the molten metal through the cavities we have inside the mold. So usually it's going to be consist of the sprue, and we're going to have the runner. The runner is the horizontal channel, while the sprue is the vertical channel. In this example, we have a mold with a sprue of 20 centimeters in long, and the cross-sectional area of its base is 2.5 centimeters square. The sprue feeds a horizontal runner leading into a mold cavity who has a volume of 1,560 cubic centimeters. Determine first what the velocity of the molten metal at the base of the sprue. Second, the volume rate of the flow. Third, the time to fill the mold. Again, you can see a question with many parameters that you hardly can know how to use them to do the calculation. So let's go back once again to the engineering of the pouring analysis. So we have several relationships that govern the flow of the liquid metal through the gating system and into the mold. This is actually what we have in the question. You can see that this is the sprue. It's have the flash at the top there just to be sure that there will be no pouring for the metal around. We pour the material. We want to know what will be the velocity at the bottom here. The length we say is 20 centimeters, and the area at the bottom is 2.5 centimeters square. An important relationship for any flow is going to be the Bernoulli theorem, which states that the sum of the energies, like the head, the pressure, the kinetic, and the friction, at any 2 points in the flowing liquids are going to be equal. And this can be simply written as the following form. The height 1 plus the pressure 1 over the density plus the velocity 1 squared divided by 2 multiplied by the gravitational acceleration plus the friction force is going to be equal the same the amount of this energy in the second state. H is the head in centimeters, P is the pressure of the liquid in Newton over centimeter square, rho is the density, the V is the flow velocity in meter per second, G is the gravitational acceleration constant, and the F is the head losses due to the friction in centimeters. And the subscript of the 1 and 2 indicate the any 2 locations of the liquid flow. So Bernoulli equation can be simplified in several ways. If we ignore the friction losses and to be sure that the friction will affect the liquid flow through the sand mold and assume that the system remains at atmospheric pressure throughout the process, so simply the equation can be reduced to be the head 1 plus the velocity 1 squared divided by 2g is equal to the head 2 plus the velocity 2 squared divided by 2g. This can be used to determine the velocity of the molten metals at the base of this sprue. So let us define the point 1 at the top of the sprue and the point 2 to be at its base. If point 2 is going to be used as the reference plane, then the head of that point is going to be equal to the 0, or the H2 is going to be the bottom. H1 is going to be the height, which is the length of the sprue itself. When the metal is going to be poured into the pouring cup, that's the pouring cup, and overflows down of the sprue, its initial velocity at the top is going to be 0. Then we only need to know what will be its velocity at the bottom. Now we can see in this equation that will be 0 and that will be 0. So simply I can say that the h is equal to the velocity 2 squared divided by 2g. Then I can find the velocity too. Okay, so this will be the equation. I can rearrange it, and then we can simply find that the velocity at the bottom is equal to under square root of the 2gh. V is the velocity of the liquid of the metal at the base of the sprue, and meter per second. G is 981 centimeter per second square, and the h is going to be the height of the sprue in centimeters. Okay, now we know how to find the velocity. That's what's part number one. Another relationship of importance during the pouring is going to be the continuity law, which states that the volume rate of the flow will remain constant throughout the liquid. Okay, so whatever liquid I'm going to put at the top is going to be the same liquid the flow rate I'm going to get at the bottom. Nothing will be lost. So the volume flow rate equal to the velocity multiplied by the cross-sectional area. Now let's try to think about that. Let me sketch something here. If I'm going to have a pipe that have a certain cross-sectional area, and I'm going to run a liquid inside at a certain velocity. So this area is going to be in meter per second. Sorry, meter square. And the velocity is going to be in meter per second. So if I'm going to multiply the V by the A, I will get the unit to be cubic meters per second. Cubic meter is the unit for the volume. Per second, that will make it as the volume flow rate. So the continuity law can say that the V1 multiplied by the A1 is equal to the V2 multiplied by the A2. That's common things, right? Q is the volumetric flow rate, and we have the V is the velocity as before. The A is cross-sectional area of the liquid, and the subscripts refer to any of the 2 points in the flow system, like the beginning and the end, or the beginning and the middle, or the middle and the end. Thus, the increase in the area will result in the decrease of the velocity, and the vice versa. So assuming that the runner from the sprue base to the mold cavity is going to be horizontal, and therefore the head edge is going to be the same as we have in the sprue base, then the volume flow rate of the flow through the gate and into the mold cavity will remain as the velocity multiplied by the A at the base of the sprue. Accordingly, the estimated time required to fill the mold cavity will be simply equal to the volume of that cavity divided by the volume flow rate. Let's try to put the units in. Here we have, let's say, cubic centimeters. Here we have a cubic centimeter per second. By simplifying, the time is going to be in seconds. The mold filling time computed by this equation must be considered at the minimum time. And this because that the analysis ignores the friction losses and possible construction of the flow indicating system. Thus, the mold filling time will be longer than what's given by the equation above. Now let's go back to the question and highlighting the parameters. So let's go back once again to the question and color it. We have 20 centimeter long, that's the H. The cross-sectional area is 2.5 centimeters squared, that's the A. The spur feeds a horizontal run leading into the mold cavity, who's going to have the volume of 1,560 cubic centimeters, that's the V capital. Determine first the velocity of the molten metal at the base. Okay, now remember the equation is V equal to under square root of the 2 multiplied by the GH. V, the volume flow rate of the flow, that will be the velocity multiplied by the area, and finally the time to fill the mold, and this will be equal to the volume divided by the Q value. So we start with the velocity first. So we said that the equation 10.4 is going to be used, 2 multiplied by 981 multiplied by the edge of 20 centimeters. And thus, the velocity is going to be 198.1 centimeter per second. The volumetric flow rate, the velocity multiplied by the area. So now we know the velocity 2, and we know the area 2. We have 198.1 centimeter per second multiplied by 2.5 centimeters squared. And this will make that the Q equal to 495 centimeters squared per second. Finally, we're coming to the time required for the filling of the mold, where the volume is 1,560 centimeter cube. So now we have the volume divided by the Q, and we're going to get the answer to be equal to 3.2 seconds. That's it. That's how we do the calculation for the time required to fill the cavity. Just remember, this is the minimum. Okay, well, that's just repeating the thing. Thank you very much, and we'll get